Hey, we have here today an interesting integral from the UNSW Integration Bee 2022. This was knockout round 3, problem 1. We have the integral from 0 to infinity of dx over x plus 1 over x squared. Okay, now I've actually done quite a few problems like this with the x plus 1 over x situation in the denominator, but this has got a little bit of a twist to it, so I think it's still going to be pretty interesting. So what I'm going to want to do with this is a u substitution, and it's a little complicated to explain, so let me just maybe get going with it and see how it goes. So I'm going to want to start a u substitution to be x plus 1 over x, and I'll take a derivative, and we're going to get 1 minus 1 over x squared dx. But now something interesting with this expression, now if I just multiply this out, we're going to have x squared plus 1 over x squared, but then multiplying the inner terms together, we're going to have a plus 2 on this. Now notice if I did another substitution, which I'm going to call, let's say, we'll use different variable v, we'll say v equals x minus 1 over x. Now if I square this, our v squared, that's going to give me x squared plus 1 over x squared minus 2. Well, notice if I just add a plus 4 on both sides of this equation, we have v squared plus 4. So v squared plus 4 is going to be the same thing as our denominator. And so that's why this substitution can be useful as well. And so let's just take the derivative of this one. So we're going to have dv equals 1 plus 1 over x squared dx. Now at this point you might be wondering why I've got two substitutions going on. I just got one integral here. Well, the interesting thing here is if you look at this term and this term, if we add these together, right, the 1 over x squareds are going to cancel and we're just going to end up with 2. So I'm going to try to use this and rewrite my integral. And what I'll do is try to put these in the numerator in order to set up my u substitution. Okay, so now I've rewritten it with these two terms in our numerator here. Just noticing though that I have changed it now because this here in the numerator is actually 2. And notice right here we have a 1. Well, that's really easy to fix. All I need to do, I'm just going to multiply it by 1/2 out front. And now this integral is equal to our original. So now all I need to do is just kind of split this into two integrals, noticing that we've set up our substitutions already for each of these. So each of these integrals should be pretty easy to do. Now, one thing I wanted to do to actually make this work, now notice we have, for this second one, we want to use our dv. So this is our dv right here. But what we want is something with v in the denominator. Well, what I need is I just need this formula here. I just want to transform it into this form so then our v substitution is going to make sense. Okay, so now at this point, you notice we have our dv in the numerator. This here is going to be our v squared plus 4. And then over here in this first integral, you'll notice this here is exactly our du value. And this is going to be in the denominator just u squared. Okay, so now for this first integral, we're going to have a 1/2 out front. And then for our integral, we're just going to have du over u squared. But I'm going to write my u squared as u to the minus 2 du. And now there is one issue with this u substitution. If I plug in infinity here for my x, well, this u is going to infinity. If I plug in 0, we're also getting infinity. So we end up with an integral from infinity to infinity. So I don't really want to do that. So I'm just going to do this as an indefinite integral and then back substitute later. And I think it's going to work out a little easier that way. And then for the second one, we're going to have our 1/2 out front. And then for our bounds, we take an infinity. When you evaluate infinity for x here, this v is going to infinity. And then we plug a 0 in here, we get 0 minus 1 over 0. So that's going to be going to minus infinity. And again, this integral is just going to be dv over v squared plus 4. Okay, so here I'm just going to look at this first integral. We're going to have 1/2, and then integrating this, we're going to have u to the minus 1, and then we need to bring a minus out front here. And then we're ready to back substitute for u. Now let me just do something here with our u value. If I get a common denominator here, and we multiply by x over x here, we're going to end up with x squared plus 1 over x. So our u to the minus 1 is the same thing, of course, as 1 over u. Well, we can just take the reciprocal of this, and we have x over x squared plus 1. So for this value, we're going to have minus 1/2 x over x squared plus 1. And now at this point, I'll just bring back my original bounds, 0 to infinity. So let's write that in there. And then evaluating this, we'll have our minus 1/2 out front. Now when we evaluate this at infinity, you'll notice we'll end up with infinity over infinity in undeterminate form. Now you could do this a couple ways. You could do L'Hopital's rule in order to find the value of this, or you could kind of just look and notice the power is higher here in the denominator, which tells me that this expression is going to 0. Then evaluating at 0, we're going to have 0 over 0 plus 1 is 1. 0 over 1 is just 0. And so, of course, this is 0, so the whole thing's going to be 0. And so this first integral is just going away to 0. So we just need to find this piece in order to finish this off. Okay, now back to the second integral. We're going to have our 1/2 out front. Now, you notice this integral is in the exact right form for arctan. Let's just consider this 4 like 2 squared, and then we can use our arctan formula. So that's going to be 1 over this value out front. So we're going to have 1/2 arctan of our variable v over 2, and this is going to be evaluated just from minus infinity to infinity. So evaluating this, I'm going to have 1/4 out front. Now with infinity, this 2 isn't going to do anything, right? So when we evaluate this at infinity, arctangent at infinity is going to be pi over 2. And then arctangent at minus infinity is going to be minus pi over 2. But minus and minus is going to cancel. We add these together and we get pi. So pi times 1/4 is going to give us our final solution of just pi over 4. Okay, that's it. Thought it was a pretty good problem today, so we'll stop it there. Thanks everyone for watching. Have a great day.